Okay. So thank you for accepting our study. Actually, I should say that we still working and it's a project ongoing. We still obtaining result. This is not a final. And I would say that this is a project, the first time that we deal with AHR kind of data. It was so interesting and challenging. I would like to thank my PhD student Daniel that he did most of the work. We're just presenting the work, and my collaborator Borjo Bakir. So I'm not sure if it's that related. I'm a little bit sick. I'm not sure if it's something related to HR, but this is what happened. I came healthy to France. Okay. Ah, like this. No? Okay. So I will not go deep in about machine learning. I assume that everybody know the machine learning, and it's become very popular recently after the ChatGPT and all of these tools. So machine learning is very important in also in all the field, and especially also in electronic health records. So it can be also used for clinical information, like using the patient demographics, medical history, current and past diagnosis, just using all of this information that exists and make sense of this data, and using the machine learning and develop some model. It's really very interesting issue. So actually, what we maybe start to think about how to predict a sequence. So a sequence, there's a visit. So we would like, I will explain the data later on, how we deal with the data, but we would like to be able to predict the endpoint that's specified by the author or by the producer of the data. So then the first thing that we start to think maybe to think how we can use some machine learning or any algorithm that able to predict a next step, like maybe ChatGPT and all these tools. But actually, we have no experience with this kind of algorithm model. What we have done is we switch the idea that we bring the data to our knowledge to use traditional machine learning algorithm, and this was very challenge. And to be honest, we find this publication just recently after we actually did our project. So also this study did some work about how to do some sequence prediction using decision tree. And decision tree is actually maybe the nature to use it in order to predict, because the decision tree, the model of tree, can be the node is actually the maybe the visit, and then actually to predict all this sequence by the tree to travel all over the tree in order to predict the final endpoint. So actually, in order to do that, one need to proceed do two steps. One is transforming the sequence data, and as you see, in order to do that, transforming the sequential data into a vector space data set in a vector space, if we are able to convert all the visits into vector space, then we're able to use machine learning. Actually, if I want to make it a very simple word, if you just take all the visit and you just convert somehow to a table, where is the column actually the features and the rows are the visit, then you are able to, and the endpoint can serve as the class label. In this way, actually, you can use any machine learning algorithm to try to predict. When we try to do all of these steps that I will explain it in details, we were not sure it really worked. We were not sure that this kind of model will work in this kind of data, and surprisingly, the result was so great. I should say that in the beginning we get a very overestimated results. I'm not sure what happened. We're still trying to figure out what's going there, but I will show you all the reanalysis that we have done. So our objective of this research that we assume that we have the given data, the challenge data, and we would like to predict the endpoint. So actually, we suggest decision tree as a model, but you will see that also we use many feature selection and many machine learning algorithm to end up with the most algorithm that provide the best results. So this is some summary. I'm not sure if it's fit exactly what we have seen before, So because we are, according to the challenge, we assume to focus on these endpoints. So endpoint 910, it's heart disease, chronic kidney disease, which is 1401. Each disease has its endpoint code, and we were supposed to deal only with this endpoint according to the challenge. And actually we have 1, 2, 3, 4. And there is also some visits that they have no endpoint, none. So we also have it. We will use it as a negative somehow. So this is the total number of records. Records, it's a visit. So as then actually we did all of the pair analysis that we assume that, for example, the 910 is the positive and the other are negative. So for each for each record that have the endpoint 910, we consider it as a positive, and the rest will be as merged to the negative pool. And similarly, we have done with the 1401 and with the rest, and so on and so on. Also, we have some triple endpoints where we have three in the same record, and this is the values. This is just to see what we have in terms of endpoint in our data. So what our methodology is like this. We have a JSON file. We would like to actually convert this into table format. So we repeat all of this process for each visit. So each visit actually, or column, or whatever you can call it, row. So we repeated. First of all, we perform column cleaning by removing empty visits. I will show you some examples. Visit with no pathology. Some visits they have no pathology. Each visit recording now we have, as you see, the Y and the X. The X actually the age range. Actually, this is the structure of the data, and the Y is actually the pathology code. Some of them actually also have more than pathology code. What we have done, we split it in the same visit. We split it into number of visits in the same visit. So then we aggregate all of this column, and labeling actually the endpoint 1401 and all of this, and the none actually also assigned to each record. Then we perform some record cleaning by, for example, empty record, we remove it. Record with no gender, we remove it. Also, the endpoint, we actually take it out in order to have the label of the data. And then we did some vectorization process by generating the unique visit. So all of the unique visits that they have, that means all of this combination of the visits and the pathology code. And then actually we keep the retain visit order, because we need the order in order to try to predict the sequence in terms of visit. Then we represent all of the data as vector space. In this stage, actually, now we have a tabular data set where actually the column have the features and the rows have the visits, and this way you can apply any machine learning algorithm. And then we train not just random forest, we train a lot of machine learning algorithm. So just for example, to give you some, each row represents a patient with multiple visits. For example, the T222 is actually the gender. Each actually record tribe is start by the gender, or 111. The visit is look like this. 106, for example, is the age. This is actually the code of the age. So it's range, for example, by less than 10. All of this you see 100, it's the range until 109. This is the age. And then actually the 1302 actually belong to the pathology code. We have 83 code like this one. But again, we just focus according to the challenge in those 4 endpoint. And as you see here, the code 111 is male and 222 is actually the female. Okay, if you just look to the data, because actually I have some problem with colors, I ask my PhD to put it in numbers. For example, if you look to the record that have no gender, like 1, so for example, this one is missing gender. I'm not sure why. Maybe the producer of the data can take care about all of this stuff. And 2, for example, empty visit. If you look, for example, number 2, there is some empty visit. I'm not sure why we have it. If there is some sequence, why we should have empty visit. Anyway, we dealt with all of this information. Switch order, like a 3. Some of these, for example, we saw that first of all the pathology code and then the age. Also, we switch it. For visit with no order, with no code. Some of them, there is no code, for example. 106, we have only the age and we don't have the outcome. Maybe there is no endpoint here. And for example, visit with the one code order like 6. And we have also with multiple like 7. So then we need to split it out. And 8, visit with endpoint, which is actually what we are looking. So we look to the data, we try to figure out what's going here. All of this stuff we're supposed to deal with them and take care about them. So in order to do that, this is actually the steps that we took in order to clean the data and to fix whatever we can. So for example, for visit number one, actually we keep the visit number 1 because we need it in our model. So for example, if you look to the this one 402.107, actually it's actually a reorder because we would like to have the age first of all and then the endpoint code. So we switch it. And what else? For example, this one 105 actually was removed because there is no any code, patient pathology code. This one actually was removed because it's empty. Also, this one was a cleaning. And then we have another condition, reordering visit. For example, as we said, we order this to have the age and then the pathology code, the age and the pathology code. And if you look to this one, actually there is some visit that have more than pathology code. Then what we have done, actually we split it into 2 or more, whatever we have there. And we keep the number M, which is actually the visit, in order to be able to use it as a sequence in our model. Okay, so now if you look to the this matrix, now for each visit we have the gender, we have the visit number 1, visit number 2, and so on and so on. And then we have the endpoint, or each endpoint that we have interest in, we took it and we put it in the endpoint because we would like to use it as a label in our model. Then actually, if you look now, you will have, now we actually move from all of these record visits to tabular data, where we'll see the features actually is the all the combination of age and the endpoint, or what the pathology code, or the this is actually the visit. We convert all of the visit to feature space, and we keep all the endpoint information. For example, if you look, see here, for example, for X1, Y1, this is what's happened in visit number 1. And this is what's happened for example number 3. It should not be in the sequence. We switch the information now for each pair, for each information of age and endpoint, we keep where is actually it's happening, in which number of visit. So the third one, this was happening in the fourth one. Just its example, this is what's happening in the fourth one. This is what could be because we split it some in the same time. So sometimes you will see 2 values in the same row because we split it, the one that we have the more than patient code, diagnosis code. And in this way, actually now, if you look to the data, we convert all of what we have before to a tabular data. You have just see, this is the one row, second row, and you have the features here, and we have the label here that we can play now, to some of them to consider as positive and some to consider as negative. So for that, after we actually convert all the given data into tabular data set, we apply feature selection. We apply different feature selection. Over also we combine it with over machine learning algorithm like AdaBoost, the decision tree, LogicBoost, random forest, XGBoost. We try many number of features. For example, we try 25 features, 50 features, 75, 100, and so on, to see if we add more features, if we can improve the performance or the accuracy. We actually found that 50 is actually for this analysis enough. We did a lot of results. We did all of the combination that we can. If you just look to the matrix, you see 25, 50, 75, for example, for each pair. And then you have the feature selection model, all of the machine learning algorithm, and all we have also report about accuracy, sensitivity, specificity of measure, precision, area under curve. If you just look to the data, you see that actually we use just 5% of the data because really we didn't have the powerful machine in order to do that. So we start by 5% of the data, which is also a huge number, and then we increase it when we decide which model we will use for further analysis. Then we used 20% of the data. I believe maybe if we can just somehow have the powerful maybe computing machine, then we can use the whole data set. For now, just we do that for 20%. So we did a lot of results like this one, and then we end up doing all of this analysis. Now, if you see, we consider just 50 features. And for example, if we now try to report about the binary classification problem, as we said, we consider, for example, the positive as the endpoint 701 and the negative is 91. So we did all of the pair. The accuracy, for example, the area under curve, we reach about 75, where actually XGBoost was the feature selection model, which was giving the best result because that we focus in this feature selection approach. And we apply it with the different machine learning algorithm, AdaBoost, decision tree, dispute, random forest, and all of this. And if you look here, for example, you see the other positive pair of positive and the negative we consider, for example, the 140. We try to see if we can distinguish between the endpoint itself, each pair like this. And we did that for all the pair that we were focusing. I think according to the challenge was 4. And for example, we start to see we have good area under curve, 75, 64. And actually, if you look to the none actually, this is the negative, where is actually missing data there. We use it as a negative data after we consult with you. This is also another experiment where actually we consider the positive as 910 and the negative all the other endpoint like 701 and the rest. And again, we report all of these results. Actually, if you look here, actually we start to see good result, 83 area under curve, when we consider the positive as the endpoint 910 and the negative 199. I'm not sure why. It's really need a lot of deep analysis, and maybe we need maybe another person to try to understand all of this in terms of medical stuff, and so on and so on. And also, if you look now, for example, for the positive 199 and the negative 910, also we reach very high area under curve, 86%. And for 199, also we have 83%. It was very interesting to see the endpoint when we consider the positive class as the endpoint 199. The performance is getting high. I'm not sure why. Again, we need to do a lot of analysis here. And if you look again, we use just 50 features, sampling 20% of the data each time. And just to be aware that each time we select 90% randomly, which could be also, there is a lot of variety here. Maybe we need to fix maybe amount of the data and then we redo that, all of this analysis. Again, similarly, we done the similar for 140 as the endpoint, and we did all of this. If you look to the summary table, this is the summary table for all of the results that I showed you before. 140, you see the area under curve, we're reaching 82, maybe the best one. 199, actually, we also getting very high results comparing to the other. 910, similarly, and 70. This is actually the performance that we have. Also, we done that for another way that we use actually the positive 1401 or 70 or 1, all of this endpoint, and the negative actually all the rest. So 1 against the rest. And also this is the result we have achieved. It's about 72 area under curve, 75. Again, 199, actually, it's interesting that always we're getting very high results. again, we should understand why, and 78 for the other one. This is actually the summary for when we use the positive one of this, the endpoint, and the rest, all they will be considered as the negative. Okay, we try now to see if we draw the decision tree, what we can see. Just to see, for example, the decision tree is huge because the accuracy is not so high. Actually, it's very big decision tree, but we try to see if we can look to the decision tree, for example, 1401 against the remaining, and to see if we can just, for example, walk through the decision tree, if we can just make all of the prediction. For example, if you just look to the 1070 as the age and endpoint 913 or the code, if the age actually, if according to this one, if it's actually, we should also not use the numerical. I will show you another result. If the value is less than 0.1, actually we consider, for example, the other endpoint, actually the number here is the sequence, the one and all of these that we have it here are the sequence. We try to see actually the endpoint, the combination of endpoint and the sequence, if we can just make some prediction. According to the tree, this can be also served as a model for prediction, the final endpoint. This is the other side. So it's so complicated. Anyway, again, it's need really a deep analysis to understand what's going here in this big decision tree. Also, we try to consider the sequence as not numerical value, as a categorical value. This is the outcome that we have. Then actually you see maybe somehow different results, but this can show you the trace of the point with the age, and the value is actually the value again is the visit, and we can use this combination in order to predict the final decision, the final endpoint. This again, when we consider all of this as a categorical value, the tree also look different. Actually, we obtained this figure just recently, and really don't have time to explore it more and more. So the last section, actually, now we have features for all the algorithms actually we run. We have a score, or we have a weight for each for a feature. And the feature are actually, just to remind you, is the pair of the age and the visit, the age and the pathology code. So according to all of this result, for example, the first one show when we consider the positive, the 1401, the negative 703, this is the top 50 features selected by our model. And the other actually is for the other analysis, the third, the fourth, and so on and so on. So again, this is really need also deep analysis to see what is the meaning of why this top 50 were obtained, not the other. And if we try to see according to this analysis, when 140 considered as positive and the other as negative, we found that we count how many times each feature appear in this 5 experiment. We saw, for example, 107, the age, and the pathology code 913 was appearing 5 times in all. It means that this code somehow very important for prediction. And then we have the other that appear 4, 3 in frequency, and so on and so on. And the rest actually appear in one of these experiments. This is also the top features when 910, the code 910 considered as positive and the other negative. This is the 50 also features. And again, this is the cumulative results for all of this analysis. And we see now 2 of them actually appear as very important in all of this analysis. It's appeared 5 times. Maybe also we need to just not to count the frequency. Maybe also we can take the score that given by random forest or this algorithm and make the average and do the analysis in different way. As I said, we're still working and making some progress in this data. This is another for 199. And if you remember, 199 always give the best results. And you see even the features here seem to be very, very interesting. So all of these features that appear 5 times, they appear in all of the analysis 5 times, and even the list of unique features are list. So always 199 give a much better results. This is for 70. Similarly, even there is no one features actually that appear in all of them. We just see this appear in 4. So as a conclusion, we can see that we're able to run a standard machine learning in order to predict the endpoint based on previous visits. Maybe we need to think about to generate more features, or to maybe to consider. Actually, we start to consider when we have for example, one visit with more than code. We get a huge number of features, maybe 1,000 or 10,000, even 10,000, which was so hard for us to deal with that. Maybe we can think about using deep learning in order to tackle this kind of big features. Anyway, we should think that how to generate maybe more accurately the features. We still think that the features that we use very simple, even it's look somehow creative in the way that we did it, but still it's very simple. We should think about more accurate representation of the features and the visit itself, the combination. We saw that decision tree is very, very good model to visualize the model in terms of visit, pathology code, and to predict the endpoint. The other actually provide the performance. Thank you very much.
So thank you very much.
Sure.
So I didn't have in my memory all the numbers, so I couldn't make an interpretation. But it seems to me that the one
Nine.
the feature, yeah, I don't remember exactly. Amputation. So this is the worst prediction. Now this is probably because there are very few. So I mean, it makes sense.
I mean the code.
Well, you presented some summarized at the beginning. I don't remember which one.
Yes, this 199 is the amputation.
Yeah. So this is the one who is
leading the results. Yes, exactly. Okay. I'm not sure why. If there is any.
No, but I mean, because we don't have so many amputation. I mean, probably is because the management of the
this
patient.
Could be because the number of records is 959. Yes.
Yes.
So maybe this is
could be. But I know when I don't know the codes why the codes are like this. So questions.
Thank you for the nice talk. I have a question about you mentioned that your models, like you consider models like one of the endpoints was a positive and rest all were negative. And for each of the models, like when you consider different endpoints as a positive one, you showed that you selected 50 features. So for each of this model, was 50 features same every time?
No, they are not the same.
So
they are not the same.
So for suppose when you consider 910 as a positive and rest all are negative, so the 50
features are not the same. The top features 50, they are not similar. If you just look to this is actually what we present in the end. This is actually, oops.
Okay.
So you see for each experiment like this is the top 50, and this is another experiment for top 50. They are not the similar. And then actually we try to summarize it. If they were similar, we will see that all of this appear in 5, but they are not similar. But there is some common, at least. This is a very good question. Actually, I did not present the common features between of them.
Yeah, because when you showed the AUROC, I was a bit confused about. And another, like, how did you split your data, like
90%, 10%.
And was it a random split?
A random split, 100 iteration.
And what do you think about data leakage there?
Second,
between training and the test set?
Second,
what about the data leakage between training and the test set?
Data what?
data leakage between your train set and the test set. When you calculate your performance AU rock or something, you might be calculating it on a test set, right?
No, we just calculate
you
the
did a
performance
cross-
in the test set, not in the training set. We train the model in the training set.
Yeah, and how was your how did you split your data between train and test set? This is what I'm asking.
As I said, 90% for training.
Yeah, but 90% randomly
Randomly.
chosen.
Random. You mean if we make equal size?
Yeah, so like some stratified strategy did you use to, because I don't
yes,
know.
no, yeah, okay. I forgot to put this information, but if I because the number are there is, you mean if we deal with the ambulance data set? If I remember correctly, we do the equal size from each. For example, if you have the ambulance data set, we took the equal size between the two, and then we run 90%, 10%.
Okay.
We balance the data.
Okay. Yeah. Thank you.
Sure. Yes.
Yeah, but we have a question from the audience. Say, good talk. Why don't you use RNN? I think this recurrent neural network. RNN-based model to capture the temporal pattern.
If we use it,
Uh,
we don't use it.
Why?
Because
you have not used it.
So I suggest to use this model. Could be, as I said. I said in the end that we should think about how to try to figure out more maybe robust or maybe better way to represent this data in terms of feature. It could be a good idea, but we didn't.
Okay, so
why I don't know.
Nice talk, thank you. I have one comment and one question. Regarding AUC, we also observed that when the data is imbalanced, the AUC values could be not reliable. Sometimes it's too high, but because of which one is the positive, which one is the negative. Like we observed that F1 score or Matthews correlation coefficient, those kind of metrics are more robust to the imbalance cases. I just want to mention that as a comment. Maybe others also observed something similar. And I also have a question about the feature selection method. When you do the feature selection, do you do this on the entire data?
No, we do it in the training part.
On the training part, okay.
In order to avoid overfitting.
Yes, thank you.
Sure.
Any more questions? No.
Thanks for a nice talk. I just have one small question. Do you have access to death registries or what sort of follow-up you have on these patients? Just as I'm thinking that it might be nice to incorporate a more survival-based model that takes into account death, because obviously one reason why somebody might not progress to chronic kidney disease is because they've died after a certain visit. Were you able to incorporate that? No, okay.
Actually, this is the
simulated data.
Simulated data.
This, I mean, is what we can. I mean,
you can simulate the
that's
data.
the idea. The idea is to simulate more and more. Next year, we will say later, but the next year we plan to include, apart from this sequence of visits, analytics and prescriptions. So we'll have a more detailed description of any patient. So probably prediction will be better. More questions?
I think that this is also happens that some records are empty or they don't have sex. There are very few, but we decided not to pre-process or post-process the model. It's just as happens because from time to time the model does the things wrong, but also in the real database things are from time to time wrong. So this is why.
We just remove it.
Yes, and we didn't remove it. The idea is that also, like CAMDA, in the CAMDA spirit, there is that you can do propose, for example, cleaning tools, etc. So okay.
Yeah, this is part of the process. Actually, sometimes we found in real records, for example, a woman with prostate cancer Say, what?
Okay.
or vice versa, men with ovarian cancer. That's, I mean, it's not frequent, but it happens from time to time. There are
Okay.
errors. So one first thing that you have to do is to clean the data first. So we have to clean also synthetic data.